Good morning. This is Michael Dong, and here is episode number 6 on HPLC peak resolution. Here is the agenda. We have 3 topics to be discussed. First one, why is peak resolution so important? And when is resolution not important? Second, we want to discuss the resolution equation shown here and what does it really mean. Third, does this peak resolution equation actually works? In this slide, we discuss why is peak resolution so important and when it is not. First, to reiterate our goals in HPLC separation, it is a physical separation technique and it's primarily used to measure the level of its constituent component in a sample mixture. Separation scientists are obsessed or really pay a lot of attention to resolution because any coelution or partially elutioned peaks would lead to inaccuracy data using UV detection. And this is because UV detector responds to any component with absorbance at that particular monitoring wavelength. Number 3, the gold standard of resolution is 1.5, which is actually called baseline resolution, leading to more accurate quantification for each peaks. Number 4, when is coelution not important? Okay, there's one scenario which would illustrate in the case study in next slide. A coelution is acceptable using UV detection if the interfering component has no absorbance at that monitoring wavelength. Here's one case study to support our statement that in some cases coelution is okay with UV detection if you're using a wavelength with no absorbance for the interfering compound. So this case study came from a validated method using UHPLC with UV detection for sinusides in an OTC over-the-counter laxative products. Uh, we have developed and validated a method for a Sandocat drug product using a wavelength of 270 for tablet. However, we change it to 340 for syrup to eliminate any interferences from some of the preservatives only found in syrup. Here is the operating summary using this column, this mobile phase, which is mass spec compatible. The UV spectrum of UV sinusides, UV spectrum of the sinusides shown here, with the lambda max at about 268 or 270, and another lambda max at about 340. Now, since the API or active pharmaceutical ingredient is a natural product with many different components, to assay the potency of the drug product, we actually summarize 8 of the major sinusides shown here in the green component. This is the structure of sinuside A. Another major one is sinuside B, which is an isomer, and with other major sinusides shown here as the green peaks over here. Rhine is the degradant. Now, it turned out that with the methods being validated at 270, we like to use the same method if possible for a different drug product, which is a syrup. Unfortunately, for a syrup component, there are preservatives being used, which is sorbic acid, methylparaben, and which actually interfere with some of the API components. Now, instead of actually changing and trying to separate uh, these preservatives from the very complex APIs, it's actually much more smarter to just change the wavelength, right? So after changing the wavelength at 340, where there's no absorbency of the preservative, the method is validated for the syrup sample without a major redeveloped efforts. In this slide, we explain the resolution equation and know that the resolution equation is really applicable for isocratic separations only. And what are the implications, right? Here's a resolution equation that commonly one of the most important equations in liquid chromatography, where the resolution, the peak resolution, is a contingent on three major factors. One is efficiency. Know that the efficiency factor is the square root of the plate count over 4. The second one is retention. Okay, the retention factor is K over K plus 1. Know that if when K is 0, there's no resolution because everything is diluted with the solvent front, right? So K cannot be equal to 0. The third one is called selectivity factor, which is alpha minus 1 over alpha. Here are some of the implication for resolution, right? The goal of most HPLC separation is to achieve resolution for all key analytes with a resolution baseline over 1.5 if possible. N is plate count or column efficiency. Typically, the estimation for plate count is equal to the column length L divided by 2 times the particle size. So a longer small particle column with high efficiency is really desirable or required for complex separation because it would improve the overall resolution of all the components. K is retention factor, and K is dependent on the percentage of mobile phase B. Now note that the factor K over K plus 1 is rapidly approaching unity when K is equal to 10, right? So when K is equal to 10, this factor is equal to 10 over 11, which is approaching unity. So this, by increasing K, it's not very effective in increasing resolution because rapidly K would be approaching a point of no diminishing return of equal to unity. Alpha is selectivity. Alpha is actually the most important factor in method development. And alpha is dependent on bonded phase and the mobile phase factor, right? For example, changing from C18 column to polar embedded column would change alpha. And changing mobile phase A, pH, ionic strength might also change alpha, or mobile phase B from acetonitrile to methanol. Here's another case study showing the effect of K prime. Okay, and by lowering the solvent strength, one can increase K and therefore increase resolution and the effect of resolution. So this is a case study of method development under isocratic condition of 3 substituted phenols using an approach called the sequential isocratic steps. So here we have a sample of 7 substituted phenols. So we're supposed to have 7 peaks. In the method development, we lower the solvent strength to about 45% acetonitrile under these HPLC conditions. And at the K of 1.5, which is the latest eluting peak, we showed a separation of 5 components, which is not good enough. By further lowering the solvent strength to 35% acetonitrile, the K is increased to 5, therefore give you a higher resolution because of this relationship. This is becoming better. So by lowering another 5% to 30% acetonitrile, in the mobile phase, we do get a starting point of a good analytical method that can separate all 7 components uh, better than baseline, right? So this is a case study courtesy of Sopelco. In this slide, we illustrate the effect of solvent type on resolution. So to illustrate by changing selectivity by using different mobile phase B, uh, the three common one are methanol and acetonitrile and possibly also THF. And they do have different solvent property leading to different selectivity. Note the selectivity factor is alpha minus 1 over alpha. And alpha is always pretty close to 1 because we're looking at two components of a close retention factor. Alpha is always pretty close to 1. Looking at the illustration of the case study, using 40% acetonitrile, we have an alpha of 1.07, a partial elution. Methanol is better in this case, 1.19 alpha, leading you to an excellent resolution. And THF is a stronger solvent, so you actually need less THF, 30%, and the alpha is actually 1.3. Please note that changing alpha is one of the most effective way to separate critical pair in a process called selectivity tuning, which is the foundation or fundamental in the traditional HPLC method development approach. Know that changing alpha from 1.1 to 1.2 would actually double resolution, right? Because the resolution is proportional to alpha minus 1, right? So it would double the resolution by changing a little bit of the alpha. Let's examine the resolution equation in more detail and see how the three factors affect resolution in the graph. So once again, we have the resolution equation, which is dependent on three different factors: efficiency, resolution, and selectivity. Know that the relationship to efficiency to the square root of n, meaning that if you double the length of the column, you can expect an increase to the square root of 2, which is about 30% increase in resolution. However, by doubling the column length, your retention time or your analysis time is also double. So it is a good way for complex mixture, but perhaps not very effective way. Retention is good for isocratic separation. However, rapidly, if you look at the graph, it is approaching almost unity when K is approximately about 10. When the retention factor reaches 10, is basically a point of diminishing return. However, selectivity is definitely one of the best way to effectively change resolution. So once again, summarizing, resolution is proportional to square root of n. Also is proportional to k over k plus 1. So when k is 0, uh, the components are eluding close to solvent front. There are no resolution. And also, if alpha is equal to 1, 1 minus 1 is equal to 0. So if alpha is 1, there's no differential to migration, and resolution is equal to 0. We want to illiterate the selectivity. Fine-tuning is the traditional approach for HPLC method development. In this case study, we want to calculate resolution from the resolution equation. And shown in this case study, which is shown in the previous video on the theory of chromatography, where we have two closely eluding compounds, and the calculated selectivity factor is 1.3 from the ratio of the retention factor. So the case study illustrates whether the resolution equation actually works by uh, actually doing the calculation using the resolution equation and compare that to the measure resolution from the chromatogram. So using this equation and looking at all the parameter uh, with the known n, which is about 5,000, uh, k is known, and also alpha is known, right? So if you go through the calculation, we can get a resolution calculated from the equation of 3. The actual calculation using the formula for resolution, which is the difference of the retention time over the average peak width at the base, give you an actual calculated resolution or measure resolution of 2.8 from estimation from the chromatogram. So this indicated that the resolution equation does works pretty good and give you a very close approximation to the actual measure value. Finally, in this slide, we want to look at a criteria called system suitability testing criteria used in pharmaceutical analysis. This can be found in the CEDA guidelines, which is from the US FDA, Center of Drug Evaluation and Research, and also versus the reality in modern drug development, some of my comments on that. I want to point out that there are 3 common system suitability testing criteria, often cited in the USP and CEDA. That is, a resolution should be above 2 if possible, a peak tailing of the main component less than 2 if possible, and the repeatability often found is either less than 1% repeatability precision or less than 2% RSD for 5 replicate injection. However, the modern reality capable by modern equipment is a little bit different in my view. So here are some of my thinkings. So even though it's nice to get over 2 or over 1.5, over 2 is a good criteria for long-term method robustness if possible. I'd like to point out that often resolution of over 1 might be justifiable if one have a very complex drug, let's say a drug product with multiple API, that would definitely be a justifiable. You have a very complex chromatogram. Also like to point out that even though uh, a peak tailing less than 2 would be desirable, would be ideal, there are many modern NCE, new chemical entity, with maybe 1 or 2 ionizable nitrogen atoms, which make the drug highly basic. In those cases, when you overload when you increase the concentration or the injection volume of the API, it's actually very difficult to get below 2 for the peak tailing. So a peak tailing just less than 3 is perhaps a more realistic guidance. And finally, the repeatability of 2 is actually not very realistic because most HPLC equipment is very much capable of a precision less than 0.2% in a routine basis. And definitely for an equipment to be qualified should be less than 0.5%. So according to the latest USP guidance in chromatography, USP 631, the repeatability is 0.73. Is actually a more indicative of the a better criteria for system suitability testing. Here is my summary and conclusion. Okay, first one, resolution of key analyte is an important for accurate quantification by UV detection. Number 2, we have discussed the resolution equation. Note that this is only apropos, it's only appropriate under isocratic HPLC condition. And it's based on three different factors, retention factor, selectivity, and column efficiency or play count. We also mentioned that changing selectivity is the most effective, the best way to resolve too closely eluding to peak, provided their adequate retention and also sufficient play counts. We also illustrate how resolution equation can be calculated and compare pretty well with the measure resolution from the chromatogram. Finally, I want to point out that most critical methods, such as POD assay or stability indicating assay, are using gradient analysis. In those cases, this resolution equation does not apply, right? Unfortunately, because things are much more complex. Nevertheless, this isocratic resolution equation is really educational for a chromatographer to illustrate the three fundamental factors affecting resolution in chromatography. Here are some key references. First one is the book by Snyder, Kirkland, and Dolan. Second one is a more modernized version of HPLC and UHPLC for practicing scientists. A third one is also a very important book in HPLC method development, also by Snyder, Kirkland, and Gleisch. Okay, here's a quiz to test your retention. I'd like to suggest that you can pause the video and go through that and see whether you would agree to the correct answer shown here. Finally, I'd like to thank you for your attention, and I'd like to urge you to subscribe to my channel for more future videos, and also to visit my website shown here or my LinkedIn page for more resources on HPLC, and also to look at other useful information. On that note, see you in the next episode.